Richard Feynman won the Nobel Prize in Physics. He was one of the greatest scientific minds the world has ever produced. A man who helped develop quantum mechanics, who worked on the Manhattan Project, who could explain the most complex ideas in all of science with clarity and brilliance that left audiences speechless. But in 1983, someone asked him a simple question. Why do magnets attract each other? And Richard Feynman, Nobel Prize winner, one of the smartest human beings who ever lived, paused. And then he said something that should stop you in your tracks. He said he could not answer the question, not because he didn't know the physics, but because no matter how deep you go into the explanation, you eventually hit a wall where the answer simply is, that is just how the universe works. And that answer, he said, never truly satisfies. Think about that for a moment. The force you interact with every single day. The force holding notes to your fridge. The force inside. Every electric motor, every speaker, every hard drive, every MRI machine on Earth. The force that protects our entire planet from being stripped bare by the sun. And one of the greatest physicists in history said he could not fully explain it. Today, we are going to find out why. Because magnetism is not what you think it is. It is not a simple, well-understood force that science has neatly packaged and filed away. It is one of the strangest, most counterintuitive, most philosophically disturbing phenomena in all of nature. And by the end of this video, you will understand why even the people who spend their entire lives studying it still find it deeply, profoundly strange. Pick up any magnet, hold it near a piece of iron, and feel the pull. That sensation, that invisible tug between two objects that are not touching, has fascinated human beings for thousands of years. The ancient Greeks discovered it first. Near a region called Magnesia, in what is now Turkey, they found a naturally occurring rock that attracted iron. They called it the Magnesian stone. We call it magnetite, and the name magnet comes directly from that ancient Greek region. For most of human history, magnetism was pure mystery. People noticed it. They used it. Chinese navigators were using magnetized needles as compasses as early as the 11th century. European sailors adopted the compass and used it to navigate the oceans, discovering continents and building empires, all powered by a force nobody understood. Nobody knew why it worked. They just knew that it did. Then, in 1600, an English physician named William Gilbert published a book that changed everything. He had spent years experimenting with magnets and concluded something remarkable. The Earth itself is a giant magnet. The reason a compass needle points north is not because of some star or mystical force pulling it. It is because our entire planet has a magnetic field, and the compass needle is simply aligning with that field. This was one of the great scientific insights of the Renaissance. The Earth is a magnet. The compass works because of physics, not magic. But Gilbert still could not explain why magnetism existed. He could describe what it did. He could not explain what it was. That question would not begin to be answered for another 2 centuries. In the early 19th century, a Danish physicist named Hans Christian Ørsted made an accidental discovery that would reshape our understanding of the universe. He was giving a lecture demonstrating an electrical circuit to his students when he noticed something strange. Every time he switched the current on, a nearby compass needle twitched. Every time he switched it off, the needle returned to normal. He almost dismissed it. Then he started experimenting. What Ørsted discovered was that an electric current produces a magnetic field around it. Electricity and magnetism were not separate forces. They were connected. This discovery sent ripples through the scientific world. A French physicist named André-Marie Ampère immediately began experimenting further and showed that two wires carrying electrical currents would attract or repel each other depending on the direction of the current, exactly like magnets. Then came Michael Faraday. Working in London without any formal mathematical training, driven purely by intuition and obsessive experimentation, Faraday discovered the opposite effect. If electricity produces magnetism, does magnetism produce electricity? He wound two coils of wire around an iron ring. When he switched current through the first coil, a brief pulse of current appeared in the second coil, even though they were not connected. Changing a magnetic field produces an electric current. This is electromagnetic induction, and it is the principle behind every electric generator ever built, every power station on Earth, every wind turbine, every dam. They all work because of what Faraday discovered in that London laboratory. But still, nobody could explain what magnetism actually was at its deepest level. Faraday himself thought of magnetic fields as lines of force flowing through space. He could visualize them, he could describe them, but he could not mathematically define them. That task fell to James Clerk Maxwell. James Clerk Maxwell was a Scottish physicist who worked in the second half of the 19th century. And what he did was arguably the greatest intellectual achievement in all of physics between Newton and Einstein. Maxwell took everything Faraday and Ampère and Ørsted had discovered, all those observations about electricity and magnetism, and wrote them down as mathematics. 4 equations, elegantly constructed, precisely expressed. Maxwell's equations described electricity, magnetism, and their relationship to each other in perfect mathematical detail. And when Maxwell solved his own equations, something extraordinary fell out of the mathematics. The equations predicted the existence of waves, electromagnetic waves, traveling through empty space at a specific speed. Maxwell calculated that speed. It was approximately 300,000 kilometers per second. That number was already known. It was the speed of light. Maxwell stared at his own calculation and realized what it meant. Light is not a separate phenomenon from electricity and magnetism. Light is an electromagnetic wave. The same equations that describe how your compass works also describe how sunlight travels across 150 million kilometers of empty space to warm your face. Electricity, magnetism, and light are all the same thing, expressed in different ways. This unification, the realization that 3 seemingly separate phenomena are actually one, is one of the most beautiful and startling moments in the history of science. And it all started from trying to understand why a magnet attracts a piece of iron. But even after Maxwell, the deepest question remained unanswered. Why does the magnetic force exist at all? To answer that, we have to go somewhere unexpected. We have to go to special relativity. In 1905, Albert Einstein published his special theory of relativity. Most people know it for E equals mc squared. But special relativity also contains something that is far less discussed and far more mind-bending. It explains magnetism. Here is how. Imagine a wire carrying an electric current. Inside that wire, electrons are moving. Alongside the wire, there is a stationary positive charge. Let's call it a particle just sitting there in space, not moving. In classical physics, the moving electrons in the wire create a magnetic field. That magnetic field acts on the stationary positive charge and pulls it toward the wire. This is the standard explanation for magnetic attraction. We have all accepted it and moved on. But now do something strange. Change your perspective. Switch your frame of reference to the electrons, moving inside the wire. From the electron's point of view, the electrons are stationary. It is the positive charge outside the wire that is moving. In this frame of reference, there are no moving charges inside the wire producing a magnetic field. So why does the positive charge still get pulled toward the wire? The answer is length contraction. Special relativity tells us that objects moving at high speed appear contracted, shorter, in the direction of their motion when viewed from a stationary frame of reference. This is not an illusion, it is a real physical effect. When you switch to the electron's reference frame, the positive charges in the wire, which are stationary in the original frame, appear to be moving. And because they are moving, special relativity says they contract. They get slightly closer together. Their density increases slightly. The wire, which was electrically neutral in the original frame, now appears to have a slight excess of positive charge. And that slight excess of positive charge attracts the positive particle outside the wire. What looked like a magnetic force in one reference frame looks like an electric force in another reference frame. Magnetism is not a separate force from electricity. Magnetism is what electricity looks like when you account for special relativity. Let that sit with you for a moment. The force on your fridge magnet, the force that steered ships across oceans for centuries, the force that generates every watt of electricity in your power grid. It is all a consequence of the fact that space and time behave differently at different speeds. Magnetism is a relativistic effect of electricity. This is why Feynman struggled to answer the simple question. Because the deeper you go, the more you realize that magnetism is not a thing in itself. It is a perspective, a consequence, a shadow cast by electricity when viewed through the lens of relativity. But we are not done, because there is another layer deeper still. If magnetism is a relativistic effect of electricity, then what is electricity? What is the electric force? This takes us into quantum mechanics, specifically into a field of physics called quantum electrodynamics, QED. In quantum electrodynamics, electric and magnetic forces are not really forces in the traditional sense. They are not invisible hands reaching across space and pushing or pulling things. Instead, charged particles interact by exchanging particles. Virtual particles. When two electrons repel each other, they do so by exchanging virtual photons. Particles of light that exist only for the briefest moment, carrying momentum between the electrons and pushing them apart. This is the quantum mechanical picture of electromagnetism. Forces are not fields in empty space. They are the result of particles constantly throwing other particles back and forth at each other, like two people on ice skates throwing a ball between them. The act of throwing and catching pushes them apart. This picture is bizarre. It is also the most precisely tested theory in the history of science. QED makes predictions that have been verified to more than 10 decimal places. It is more accurate than any other scientific theory human beings have ever constructed. And yet, it describes a universe of constant, frenetic, invisible particle exchange happening in every cubic centimeter of space, at every moment, between every charged particle. Your fridge magnet is working because of trillions upon trillions of virtual photon exchanges happening faster than any timescale you can conceive of. This is what magnetism looks like at the quantum level. Now, let us step back from the equations and look at what magnetism actually does in the universe. Because the applications are so vast, so fundamental, that it is almost impossible to imagine a cosmos without it. Start close to home. The Earth has a magnetic field. It is generated deep inside our planet, where liquid iron in the outer core flows in complex patterns driven by the planet's rotation and internal heat. These moving currents of molten iron generate electric currents, and those electric currents generate a magnetic field that extends tens of thousands of kilometers into space. This field is called the magnetosphere, and it is the reason life exists on Earth. The sun constantly emits a stream of charged particles called the solar wind. These particles travel at hundreds of kilometers per second and carry enormous energy. If they struck the Earth's surface directly, they would strip away the atmosphere, destroy the ozone layer, and bombard everything on the surface with lethal radiation. Every single day, the Earth's magnetic field deflects billions of tons of solar wind particles away from our planet. They flow around the magnetosphere, diverted by magnetic forces, and stream past us harmlessly into deep space. Without the magnetosphere, Earth would look like Mars, a cold, dry, radiation-blasted rock with a thin wisp of atmosphere and no life anywhere on its surface. We are alive because of magnetism, the beautiful auroras, the northern and southern lights, are what you see when some of those solar particles do manage to enter the magnetosphere at the poles and collide with atoms in the upper atmosphere. The glowing green and red curtains of light are magnetism made visible. Now go further out into space. Magnetism does not stop at Earth's doorstep. It is one of the dominant forces shaping the universe at every scale. Pulsars are among the most extreme objects in the known universe. They are the collapsed cores of massive stars that have exploded as supernovae, essentially the remnant left behind after the star destroys itself. A pulsar contains more mass than our sun compressed into a sphere roughly 20 kilometers across, and pulsars have magnetic fields, not Earth-strength magnetic fields, not even strong industrial magnet fields. Pulsar magnetic fields are 1 trillion times stronger than Earth's, in some cases even stronger than that. These fields are so intense that they are fundamentally incomprehensible by any human intuition. At those field strengths, the quantum vacuum itself becomes distorted. The fabric of space in the immediate vicinity of a pulsar behaves differently from normal space. Light bends. atoms are stretched into thin needles aligned with the field lines. The physics we use to describe everyday reality simply breaks down. These objects fire beams of electromagnetic radiation from their magnetic poles with such precision and regularity that when they were first discovered in 1967, the scientists who found them briefly considered whether they might be signals from an extraterrestrial civilization. They were so regular, so precise, that they seemed artificial of large-scale magnetic fields threading through it. These fields span thousands of light years. They run along the spiral arms. They help shape how gas clouds collapse to form new stars. The origin of galactic magnetic fields is one of the open questions in modern astrophysics. We do not fully understand how they formed or how they have maintained themselves over billions of years. The processes that generate and sustain magnetic fields at galactic scales are still being studied. And beyond galaxies, there is evidence that magnetic fields exist in the vast filaments of gas that connect galaxy clusters, the cosmic web, the largest structures in the universe. Magnetic fields threading through the skeleton of the entire cosmos. Magnetism is not a small, local phenomenon. It is a cosmic force, present from the scale of subatomic particles to the scale of galaxy superclusters. Here is something that might genuinely unsettle you. We have talked about how magnetism works. We have talked about its relativistic origins and its quantum mechanical description. But there is a question that physics still cannot fully answer. Why do electrons have magnetic moments? An electron is a fundamental particle. As far as we know, it has no internal structure. It is not made of anything smaller. It is a point particle, or as close to a point as physics can currently measure. And yet electrons behave as though they are tiny magnets. They have a property called spin, and this spin gives them a magnetic moment. They align with magnetic fields. They generate tiny magnetic fields of their own. But electrons are not actually spinning. They are not little balls rotating on an axis. The word spin is a historical accident. The property was named spin because it behaves mathematically like angular momentum, but it is not rotation in any physical sense. It is an intrinsic quantum mechanical property, a fundamental feature of what electrons are. It cannot be derived from anything more basic. It simply is. And it is this property, this mysterious, unexplained, fundamental quantum spin of electrons, that gives rise to ferromagnetism, to permanent magnets, to the magnet on your fridge. In most materials, electrons are arranged in pairs with opposite spins, and their magnetic moments cancel each other out. The material is not magnetic, but in certain materials, iron, nickel, cobalt, the atomic structure is such that many electrons have unpaired spins pointing in the same direction. Their magnetic moments add up rather than canceling. And when large numbers of atoms align their magnetic moments together in what are called magnetic domains, the material becomes a macroscopic magnet. Your fridge magnet works because of the quantum mechanical spin of electrons, a property that physics can describe precisely, measure accurately, and use to build technologies of extraordinary complexity, but cannot fully explain why it exists at all. Let us bring this back to Earth, because the practical consequences of magnetism are so woven into modern life that removing it would collapse civilization almost instantly. Every electric motor in existence works on magnetism. When you turn on a fan, a washing machine, an electric car, a pump, a drill, you are converting electrical energy into mechanical motion using the interaction between electric currents and magnetic fields. Faraday's discovery made physical. Every electrical generator works on magnetism. When a turbine spins, whether driven by steam in a coal plant, by falling water in a dam, or by wind in a turbine, it rotates coils of wire inside magnetic fields, generating electricity. Every electron flowing through every wire in your home was set in motion by magnetism. Speakers and microphones work on magnetism. The music you listen to is produced by a coil of wire attached to a paper cone sitting inside a magnetic field. When electrical signals from your music pass through the coil, the magnetic forces push and pull the cone, creating pressure waves in air. Sound. Hard drives work on magnetism. The data stored on a traditional hard drive is encoded as patterns of magnetic orientation in a thin layer of magnetic material on a spinning disk. Your files, your photos, your documents, all stored as microscopic regions of magnetized material, each one representing a 1 or a 0. MRI machines work on magnetism. Magnetic resonance imaging uses enormously powerful superconducting magnets to align the hydrogen atoms in your body, then pulses of radio waves to knock them out of alignment, then detects the signals they emit as they realign. The result is detailed images of soft tissue that X-rays cannot see. Cancers are caught, brains are examined, injuries are diagnosed, all because of magnetism. Credit cards, hotel key cards, train tickets. The magnetic strip on every one of them stores information as patterns of magnetic particles. Swipe a card, and you are reading a magnetic recording. Particle accelerators use powerful electromagnets to steer beams of charged particles around circular tunnels at near the speed of light. The Large Hadron Collider at CERN, the machine that discovered the Higgs boson, uses thousands of superconducting magnets to keep its particle beams on course. Magnetic levitation trains float above their tracks with no physical contact, propelled and guided entirely by magnetic forces, reaching speeds of over 600 kilometers per hour. The modern world is built on magnetism. Not metaphorically, literally, remove it and nothing works. And yet, we still cannot fully explain it. We can describe it. We can use it. We can engineer technologies of breathtaking sophistication using it. But when you ask the deepest question, why does this force exist? Why do particles with electric charge interact through magnetic fields? Why does the electron have spin? The answer eventually runs out. This is not a failure of science. It is science being honest about its limits. Physics has always worked in layers. Each generation of scientists peels back one layer of reality, finds the deeper structure underneath, and begins the work of understanding that new layer. And each time they look deeper, they find something stranger than what they expected. Magnetism seemed like a simple, obvious, familiar thing. It turned out to be a window into special relativity, quantum mechanics, the structure of matter, and the fundamental nature of force itself. Feynman was right to hesitate when asked to explain it, not because he did not understand it, but because he understood it well enough to know how deep the mystery went. There is one more thing to consider before we close. We have spent this entire video talking about magnetism as a force humans have studied, measured, harnessed, and partially explained. But the universe had magnetism long before humans existed, long before Earth existed, long before the sun existed. The early universe, in the first moments after the Big Bang, was filled with charged particles moving at extraordinary speeds. Those moving charges generated magnetic fields. Those fields influenced how matter clumped together, how gas clouds formed, how the first stars ignited. The magnetic fields threading through our galaxy today are remnants and descendants of fields that formed billions of years ago, shaped and amplified by billions of years of stellar birth and death, supernova and neutron stars, galactic rotation, and turbulence. We are living inside a magnetic field that has been evolving for nearly 14 billion years. Every time you hold a magnet, you are holding a tiny piece of a phenomenon that has been shaping the cosmos since almost the very beginning. The force that Feynman could not fully explain. The force the ancient Greeks found in a rock in Turkey. The force that protects our atmosphere, powers our civilization, steers particles across the galaxy, and threads itself through the largest structures in the universe. It is on your fridge. It is in your pocket. It is in the ground beneath your feet and the sky above your head and the space between the stars. And we still do not completely understand it, which means the investigation continues, which means there is still something left to discover. If this video changed the way you think about the invisible forces shaping everything around you, consider subscribing, because we have only just started going deep. I will see you in the next one.